Hey folks, welcome to our factoring lecture. We're going to take a look back up with factoring, and you may have some experience with this, a lot, a little, but we want to just kind of review all those concepts that we've talked about, or hopefully you've had some experience with in a previous algebra class. So we're going to look at factoring out GCFs, or greatest common factors. We'll factor by grouping. We'll factor two terms, or what we call binomials. We'll factor trinomials, three terms. The easier version of this is when the lead coefficient is 1. The more challenging version of this is when you have a quadratic term where the quadratic coefficient is not 1. And if you're not sure what I'm referencing, right, it's easier to factor out something like x squared minus 3x minus 4 than 2x squared minus 3x minus 4, right? So this was a lead coefficient of 1. This was a lead coefficient that was not 1. These are trickier to kind of factor out. And we'll practice that. And then we'll factor polynomials with more than 3 terms, right? So we typically say binomials, 2 terms, trinomials, 3 terms, and polynomials, we usually apply that when you have 4 or more terms, or at least apply that vocab term. All right, so the first rule of factoring is always to take out the GCF. If you ever watched that movie Fight Club, which is dating myself because I'm a little older, right? First rule of Fight Club is you don't talk about Fight Club, but first rule of factoring is take out the GCF. And a lot of times we have to take out a GCF between numbers and variable terms, all right? It's a pretty common version of a factoring problem. So when we're talking about a number, we'll take that list, we'll find those numbers, right? We'll list out the integers that are common to those numbers, and we'll factor out the largest common integer, and you'll see that come into play. And then if you have a variable term, to get to the GCF, you're going to take the least exponent that appears on that variable in all of the terms. So I'll talk about that as we move forward as well. So I'm going to scooch my paper up just a wee bit so we can get some of the problems in view. All right, and we'll keep all of this in mind, right? That we're gonna have GCFs on the numbers, right? The coefficients in front of these terms, as well as possible variable terms. So if we look at this first example, right? We're gonna factor this. We've got an 8x here and an 80 here. So if I look between 8 and 80, if we just look at the numbers, right? So 8, I could break this into 2 times 2 times 2, but hopefully we're seeing that 80, I think it's easier to think of 80, I could break this into 8 times 10, right? So if we look at the number common to both of them, 8 is common to both of them, so that's going to be part of my GCF, right? I'm going to take out the largest common factor. So 8 is the largest common factor, so that's me playing out this first sentence, right? I made that list of integers, and it's the largest common factor for these integers. Now, for the variable term, I want you to see you have x to the 1 here, and you really have no x terms. You could write this essentially as times x to the 0, because anything raised to the 0 power is 1. But so you have x to the 1 here, x to the 0 here, and you want to take the least exponent that's common to all terms. And really, you have an x here, you don't have an x here, so you don't have an x common to both, right? The least exponent is x to the 0, which is essentially 1. And that might sound like it's overcomplicating things for an example like this, but that's going to play itself out in the rest of these examples. So x to the 1, x to the 0, 0 is the least exponent, so that's what I'm going to quote unquote factor out. That's part of my GCF. But on top of that, anything to the 0 is 1. So ultimately, my greatest common factor here is 8. When I remove the 8 from 8x, I'm left with x. When I remove the 8 from negative 80, I'm left with negative 10. So I can factor out this GCF of 8, right? 8 was the greatest common factor between 8 and 80. And then I had x, and I had no x's here, so I couldn't factor out a variable, which is fine. And you can always check yourself. You can redistribute to check yourself. 8 times x is 8x, 8 times negative 10 is negative 80. All right, so let's take a look here. I'm going to look at b, 2x cubed, 10x squared, 2x. So if I look at just the numbers, right, 2, 10, and 2, right, if I think about 10, I can break 10 into 2 times 5. So the only thing common to all three of these is that number 2. So in terms of my GCF, when I start to build it, right, I know 2 is going to be part of it. But now let's look at the variable terms, right? I've got x cubed, x squared, and x, right? Because I want to separate the number that I need for the GCF and the variable term I need for the GCF. And we look at x cubed, right? Exponents 3, x squared, exponents 2, x, secretly a 1 there. We're going to take the smallest exponent, the least exponent. So the smallest number between 3, 2, and 1 is 1, which means x to the 1 is going to be in my GCF. All right, so when I go to factor out my GCF, I'm going to have 2x. When I remove 2x from 2x cubed, right, the only thing that survives is x squared. When I remove 2x from 10x squared, right, when I factor that 2 out from that 10, I'm left with 5. When I factor out x from x squared, I'm left with x. And then I've taken the entire 2x out from here, so I just have a -1. And we'll talk a little bit later about how x squared plus 5x minus 1, this trinomial, is prime. I can't actually factor it right now, which is great. That means we're just going to end this problem as is. But we'll talk about this a little bit later. How can you recognize this factor, this trinomial, as prime so that you don't have to go further with the problem? All right, so I'm going to scooch this up and we're going to keep this in mind. Sometimes I need to factor out a GCF from numbers, sometimes from variable terms. All right, so if I move this up, let's see what we're working with here. All right, so I've got m to the 7th, m to the 9th, right? So I've got no numbers, right? Like in example A, I had the 8 and the 80. I don't have this. I don't have, both of these coefficients are 1, so there's not going to be a number I need to factor out. So I'm going to have to take the smallest exponent, right? I have a 7 and I have a 9. 7 is the smallest. So my GCF here is just, not x to the 7th. Sorry, we have a different letter, m to the 7th. That's fine. Let's factor out that m to the 7th. When I take out an m to the 7th from m to the 7th, I'm left with 1. When I take out m to the 7th from m to the 9th, I have 2 powers of m left over. And we will talk a little bit later about how when you have a sum of squares, that is also prime, okay? Maybe you remember a formula or hearing about something called the difference of squares. When you subtract 2 perfect squares, that can factor, but sum of squares is prime. And we're going to talk about that a little later too. All right, if I look at D, right, I've got my first term here, 12 times p minus q. I know it looks funky, but this is an entire term, right? And then I have 7n times p minus q. All right, so let's start breaking these down. Number-wise, I have 12 and 7. They have nothing in common, so there's nothing I can factor out of there. Here I have m to the 1, right? I have 0 m's over here, so in a sense you can think of this as m to the 0. So the smallest exponent between m to the 1 and m to the 0 is m to the 0, which is just the number 1, so I can't factor out any m's. And essentially there's an m here and there's nothing here, so there's just nothing to do. Same thing's going to happen here. There's an n to the 1 here. There are no n's here, right? It's essentially n to the 0. And if I'm taking the least exponent, I'm taking that 0. N to the 0 is just 1. And I think if we just kind of take a step back, there's an n here, there's nothing here, so they have nothing in common. All right, but I do have a p minus q, all right? I have that binomial to the 1, and I have another p minus q to the 1 over here. That factor, which is itself a binomial, but that factor, so if I take a look at my GCF, right, in this case, it's p minus q. So I can factor that out of both terms. Oh, let me scooch this to the side just to make sure you can see this. My apologies if this was off out of margin. All right, so as I start to move forward, let me factor out the p minus q, okay? Let's see what's left. If I factor out a p minus q from this first term, all that survives is 12m. If I factor out a p minus q from this second term, all that survives is 7n, which is fine, or really technically minus 7n. And again, you can always check this. If you were to refoil or redistribute, right, p minus q times 12m gets me this term. P minus q times negative 7n gets me that term. All right. So let's take a look. We've got a couple more. I'm going to scooch this up yet again just to get these in view. All right. And I think we're able to see everything. Okay. So if I start to look at this, let's look at E. I've got 8, 16, and 12, right? So 8, 16, and 12. If I think about what the GCF between those three numbers would be, right? This is 4 times 2, 4 times 4, 4 times 3. So I have a 4 common to them. Let's look at the P's. We've got P to the 5th, P to the 6th, P to the 4th. I need to take the least exponent, so P to the 4th. I've got Q squared, Q cubed, Q to the 7th. I need to take the least exponent, so Q squared. There's my GCF. Yeah. So let's factor that out. I have 4 P to the 4th, Q squared. And let's see what's left over. All right, 4 to get to 8 is going to be 2. P to the 4th to get to P to the 5th, P. Q squared to Q squared, I don't need anything. All right, 4 to get to 16, I'm going to do plus 4. P to the 4th to get to P to the 6th, P squared. Q squared to get to Q cubed, Q. All right, and I'm going to have a minus. All right, 4 to get to 12, 3. P to the 4th to P to the 4th, I don't need anything. Q squared to Q to the 7th, Q to the 5th. Right, so there I am factoring that out. And again, if I wanted to check that I did this correctly, you can redistribute, right? So go ahead and just multiply, distribute that. If I distribute this, if I do 4p to the 4th q squared times 2p, 4p to the 4th q squared times 4p squared q, 4p to the 4th q squared times negative 3q to the 5th, and I get back to my original expression, it's a check on myself that I did it correctly. All right, so let's see what we got with F here. Let's round this out. I've got 14, 21, and 7. So if I think about the GCF between those, the largest number they have common to them is 7. All right, I got a cubed, a squared, and a, right, a to the 1. The least of those exponents is a, right? I've got b squared, b cubed, and b to the 1. All right, the least of those exponents is just b. So there's my GCF. Now for me personally, I don't like having a lead negative. So I'm going to erase this a little bit. I'm going to take out negative 7ab. And this is a personal preference. I want you to hear, and I'll show it to you with just the 7ab in a moment, but I like to take out negative 7ab just so it makes it easier to factor later on if I have to factor later on, right? And we've been talking about how some of these are prime, right? This was prime, this was prime, this is ultimately prime. And I'm going to talk to you in later examples, how can we recognize this binomial is prime, this binomial is prime, or this trinomial is prime? We're going to practice that later on. But when I start to practice, if these remaining terms are prime, I personally like lead positive coefficients. So what I mean by that is if I factor out negative 7ab, if I take out the negative 7 from negative 14, I'm left with positive 2, a lead positive. All right, a to get to a cubed, a squared, b to get to b squared, b. If I take out a negative 7 from negative 21, I'm left with positive 3. All right, a to get to a squared, a, b to get to b cubed, b squared. And be careful, if I take out a negative 7 from positive 7, I am left with negative 1. All right, a to get to a, I don't need anything. B to get to b, I don't need anything. So I close that out, right? So that's one way to factor it. And I'm just going to put the or here. If I had taken out just the positive 7ab, I would have had negative 2a squared b minus 3ab squared plus 1, right? So both of these factorings are correct. Personal preference, I prefer taking out the negative here, so I have a lead positive here. Because in future examples, we are going to be able to factor these trinomials that are left over, or maybe these binomials that are left over. Again, we couldn't in example 1. I did that by design because I wanted them to be prime because we haven't talked about factoring trinomials yet. But for me, if I do have to discern, like, hey, could I factor this further? It's easier for my brain to work around a positive lead coefficient. All right, thanks so much, everyone. Bye.